was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
It's perhaps the holy grail of planetary science.
Are we alone in the universe? It's one of the grandest questions we could answer.
We don't really have a definition of life, but I think I'll know it when I discover it.
Life can take many twists and turns, and I think the really cool thing about it is the variety that we're going to be able to find elsewhere.
Are we a lonely planet? Or does life exist beyond Earth? Members of the groundbreaking field of astrobiology have joined forces to solve this enduring mystery. Life. Is it rare in our universe? Or is space a galactic zoo, teeming with all sorts of creatures?
Everybody has this sort of iconic view of the aliens. They're going to be little gray guys with big eyeballs and small noses. Well, maybe, but I don't think so.
On far-off planets, life may be as far out as buggy-eyed microbes or sci-fi sea monsters like galactic manta rays. Others may be home to cybernetic organisms, hybrids of biology and machines.
One way to get a handle on thinking about super advanced aliens is to try to imagine the possibilities of our own future. Maybe it'll be machine-enabled humans. I feel like I've already become a machine-human hybrid. I mean, I have this laptop computer that I take with me everywhere, which is really kind of the third hemisphere of my brain. My body's even changing and becoming sort of shaped like a person using a laptop computer, and so I'm becoming Homo laptopicus. It's likely that the universe is full of life. We don't have evidence yet that we're not alone. So we're out there and we're looking.
When it comes to hunting for alien life, planetary scientist and musician David Grinspoon walks to a different beat.
I do wonder, in terms of extraterrestrial life, whether they'll have music or something like music. Music is fundamentally waves and rhythms, and that's sort of the nature of our universe. There is a certain musicality of just the fact that it's all vibrations and waves and rhythms and modulated tones. So I can imagine, and this is just my wild fantasy, some analogy to world music far in the future where we're mixing our musical cultures with alien musical cultures. I think you'll get many different shades of astrobiology if you talk to different scientists, but I think you'll get a lot of agreement on the broad goals. We want to find life elsewhere, but in the meantime, we're learning a lot about the history of life on Earth.
In the field of astrobiology, one of the fundamental goals in searching for life elsewhere is first figuring out how life evolved here on Earth.
One of the big unsolved mysteries in astrobiology, of course, is how life got started on Earth. Because if we could understand that, then we would have some insight into whether it could have gotten started elsewhere.
Earth orbits in what's called the habitable zone. It's a region of space where conditions are favorable for life forms that we know can be found on our planet. We are at just the right distance from the sun, so our oceans don't evaporate. Our temperatures are not too hot or too cold. And we have oxygen in our atmosphere, so we can breathe. Earth's been a cosmic paradise for all types of life, from small single-celled organisms such as bacteria to large multicellular mammals, including man. It's believed that all life on our planet descended from a single common microbial ancestry, approximately 3.4 to 3.8 billion years ago. But how that microbe came into being remains puzzling. One way to search for answers is to look for ancient rocks where microbes leave trace evidence of their existence.
Geology is a crucial tool for understanding the origins and evolution of life on Earth because the historical record of life on Earth is almost entirely recorded in the rocks that we walk on.
Geologist Abigail Allwood's journey to discover the origins of life took her no farther than her own backyard. The Pilbara region of West Australia contains some of the oldest rocks on our planet. They're almost 3.5 billion years old.
The Pilbara contains rocks from the early Archean era that have survived on the Earth today. They contain several rock units that contain possible evidence for life.
Planet Earth has been around for over 4.6 billion years. But most of its original surface has been obliterated by plate tectonics and erosion. The extremely thick crust in the Pilbara has helped it resist destructive geologic processes.
The Pilbara hasn't been strongly affected by plate tectonics, and the original features in the sedimentary rocks are more or less ready for us to interpret. There are also sedimentary rocks of similar age, almost 3.5 billion years old, in South Africa. So far, the Pilbara seems to have yielded a richer fossil record.
Allwood spent more than 3 years surveying some of the rock formations in the Pilbara, examining unusual structures called stromatolites, fossils formed by living organisms 3.5 billion years ago.
We realised that what we were looking at was the remnants of an ancient reef, a microbial reef. It's not a reef made of coral like we're familiar with today, but a reef made of stromatolites, structures formed by microorganisms.
Stromatolites are rocky structures that form on the sea floor, where fine layers of sediment are built up into cones, domes, and other shapes over a long time with the help of tiny organisms. A stromatolite is not alive, but is a structure made by living things. When we find one in the fossil record, it is like finding the footprint of long-dead microorganisms. But the microbes themselves are almost never preserved as fossils inside the stromatolites. And without that, it is extremely difficult to be sure an ancient stromatolite is proof of life. But in this case, Allwood found that the Pilbara stromatolites are in fact biological. She just may have discovered the oldest evidence of life on our planet.
These stromatolites are the oldest convincing evidence of life on Earth, in these amazing pronounced conical structures that are not like any kind of wave ripple or structure that you'd expect to see on the seafloor where there's no biology. These are interpreted as stromatolites, sedimentary structures formed by microorganisms that lived at the interface between the sediment and the ocean.
Allwood used geological techniques to interpret the environment these fossilized microorganisms may have lived in almost 3.5 billion years ago.
What we saw was that immediately before the stromatolites formed was a setting pretty much just like this, a rocky coastline. We see that the stromatolites only exist in the shallow water environment and don't exist in the deep water areas that were existing at the same time.
This fossilized ecosystem provides a glimpse into the past and what might be the remains of man's earliest ancestors.
with the rise of astrobiology and new techniques and approaches to interpret evidence for life, we can be fairly confident about saying that life was on Earth at least 3,430 million years ago.
But could life have existed even earlier on our planet?
The oldest evidence of life is not evidence of the oldest life. We do not have any geologic record for the first 500 million years of Earth's history, so there's a whole bunch of stuff missing.
What's not preserved in the fossil record is how life formed in the first place. We humans are the descendants of stardust. 4.6 billion years ago, stellar debris created vast clouds of gas within our solar system. These gaseous clouds formed dust particles, which stuck together. They eventually formed large boulders made of rock and ice called asteroids and comets. For millions of years, these bodies collided and coalesced to form planets, including Earth. During this heavy bombardment, Earth was a hot, toxic water world. But in the midst of this volatile period, life may have taken hold below the ocean surface, in hydrothermal vents, which are formed near volcanoes. There, atmospheric chemicals and energy may have formed a cocktail of amino acids, the essential elements of life.
One of the popular hypotheses is that life arose around a hydrothermal vent because of the particular conditions there, that it would have been a deeper water environment which offers protection from impacts. Shallow water environments would have been very hostile during the period of heavy bombardment.
But the key question for astrobiology is, where did the spark occur that took non-living matter and turns it into living matter?
Chris McKay is a giant in the field of astrobiology. The NASA scientist has spent over 25 years trying to decode the origin of life on Earth and find it elsewhere.
There's a whole set of theories that suggest that everything needed for life started and was created here on Earth. So the organic material that led to the first life could have been produced in lightning discharges on Earth. An alternative theory is that the organics that led to life weren't created on Earth, but came into Earth. Comets, for example, could be a source of organics. Meteorites from Mars or asteroid infall could have been a source for organics. So now the raw materials are imported, but life is still homegrown. Yet another theory suggests that not only did the organics for life come in, but life itself might have come in from outer space. We don't really know how to choose between those three alternatives.
All life on Earth is made up of essential building blocks, including carbon, hydrogen, oxygen, and nitrogen, as well as 24 other ingredients. But the fundamental properties appear to be water and carbon.
The carbon in water model of biology is the one that we're familiar with, and it seems to be the best way for biology to operate.
Scientists think the best chance for finding extraterrestrial life is to search for traces of carbon and water on planets in our own solar system. Mercury and Venus are too close to our Sun to sustain liquid water or an Earth-like atmosphere. But what about Mars, the fourth planet from the Sun?
Studying the oldest evidence for life on Earth is relevant to the search for life on Mars. We have strong evidence that sometime in the past, Mars may have been more hospitable, wetter and warmer, and had an atmosphere.
Today, Mars looks like a dusty red desert. Its atmosphere is so thin that liquid water would freeze and evaporate at the same time on its surface. But Mars's topography reveals polar ice caps, gullies, and volcanoes, including Olympus Mons, the largest in the solar system. So could liquid water still exist beneath the surface, where temperatures are warmer? Scientists believe the best chance for finding life beyond planet Earth might be next door in our solar system. Mars, the fourth rock from the Sun, may have liquid water beneath its surface, a good signature for life.
Hydrothermal systems can definitely exist on Mars, though, because we can see massive volcanoes. We know there's plenty of water still on the surface of Mars. That heat source, the water source, provides all the ingredients necessary to make microbial life very happy.
To better understand the geology on Mars, astrobiologist Dr. Adrian Brown investigates the hotspots on Earth, particularly Lassen Volcanic National Park in Northern California.
The reason I'm interested in Lassen Volcanic Park is because of these hydrothermal hotspot areas where we can find minerals that are forming that don't form anywhere else but these areas. These sulfate-rich minerals that we see in the sides of the hills here are areas that we think that are analogous to Mars. And the fact that they're still active today means that we can get an idea of how friendly they are for life.
Hydrothermal hot springs are formed near volcanoes. Deep underground, the searing heat of volcanic magma chambers propels hot water and dissolved minerals into cracks and fissures in the subsurface, which then erupts onto the surface of the Earth. The spring surrounds itself with a treasure trove of energy-laden minerals suitable for a microbial feast.
A hydrothermal spring, just like the one behind me here, would be exactly the place that we want to land on Mars. This sort of area would be just perfect for life to exist, perhaps even for life to form, the origins of life. This area where water has been forced up through conduits and carried along minerals, energy sources to the surface and then spread them out around the deposit for microbes to feed on as an energy source.
Brown thinks if Mars is still volcanically active, similar hydrothermal areas will exist. They might be places where life may have originated or still exists just below the surface.
Mars is the red planet that we see from orbit, but just underneath a thin layer of dust, we see a whole rich array of sulfate-rich minerals that many scientists believe may have been formed hydrothermally. And we see those very similar minerals in the rocks and the hills surrounding us here at Lassen.
In 2006, NASA's Mars Reconnaissance Orbiter probe arrived at the red planet. It's equipped with the Compact Reconnaissance Imaging Spectrometer for Mars, better known as CRISM, which plans to revolutionize our view of the planet. Using visible and infrared light, the instrument has been scanning for evidence of ancient liquid water in Valles Marineris, a massive canyon system ripped into the surface by the volcano Olympus Mons. The area may hold hydrothermal deposits.
Mars is unlikely to be active at the moment, but in its active phase, it may have been that hydrothermal waters were driven by the massive volcanoes that we see on Mars today. And Mars may have been able to form active hydrothermal systems such as this and build up a rich layer of sulfate minerals on the surface of Mars.
Early Mars was much more habitable than the current day Mars. The planet cooled off. It's now too cold and too dry to support life. So if there was early life on Mars, it's probably not on the surface anymore, and it could potentially have migrated into the subsurface, into habitable environments below the ground.
Research scientist Jennifer Heldman is also on a quest to find life on Mars by understanding how microscopic organisms survive in extreme environments on Earth. But instead of investigating the hotspots on our planet, she scours for life in cold places.
Right now, specifically at Lassen Volcanic Park, we are looking at snowpack deposits. And we're especially interested in these snowpacks because they have snow algae living in them. So in the late spring, summer months, you'll see the snowpacks colored bright red, streaks and ribbons of red running through the snowpack. And that's the algae, so there's actually life living in these snowpacks. And so we're studying the physical conditions that the snow algae like to live in and applying that to snowpacks on Mars to see if the same conditions within snowpacks on Mars might exist.
NASA's Mars Global Surveyor has recently discovered Martian gullies that could be the ancient remains of snowpacks.
We're looking at these to study this phenomenon. Can those snowpacks actually melt, generate liquid water, and also potentially provide habitable environments for life?
To better understand snowpacks on Mars, Heldman conducts experiments in Lassen Volcanic Park.
So this is our setup for measuring temperature and light profiles through the snowpack. And what we're doing is using this instrumentation to understand the physical conditions within a snowpack that are able to support snow algae. This winter, this will get completely covered in snow and buried. And so we have sensors mounted on a pole here. So we have some moisture sensors here and here. And then these little ones are just temperature sensors. And then at the very top of the pole, we have a light sensor, which measures incoming solar radiation. And then down here, covered in the bucket, we have a tipping rain gauge. And this will measure the amount of liquid water that flows down through this bucket. The snow algae that we're seeing here thrives in these very low condition environments. It's very happy being at 0 degrees C. It's very happy in low light conditions. It's very happy in the nutrient poor conditions of a snowpack. Once we understand the conditions that support life here in the snowpack at Lassen, then we're also doing studies of snowpacks on Mars. And if we find the same conditions on Mars, you have to ask yourself the question, well, if these snowpacks on Earth are habitable, could those snowpacks on Mars also be habitable?
In addition to Martian gullies, two massive polar regions may also be places where life still exists on Mars. On August 4th, 2007, NASA launched the Phoenix Mars Lander spacecraft. When it finally arrives on the red planet in early June, it will probe its icy poles. Aboard the craft, robotic arms and dig trenches will plow through the layers of water ice to see if there are organic compounds, the building blocks of life.
We might go to the polar regions on Mars, drill down into the ancient ice, bring up organisms that are dead. They've been shelled by radiation, but we might be able to, by studying their biochemistry, patch them back up and resurrect them.
But even if Mars holds liquid water, could it have ever sustained larger animal life? When searching for Earth-like life in our solar system, scientists look for the presence of liquid water and carbon. They're crucial ingredients for life on Earth. But are there other indicators? Some scientists believe plate tectonics is necessary to promote biodiversity and act as a defense against mass extinctions. On Earth, plate shifting created continents. Without land masses, Earth would have remained a water world, and therefore, many species, including humans, may not have evolved. So why does plate tectonics exist on Earth and not on other terrestrial planets, such as Mars?
Because Mars is smaller than Earth, likely its interior cooled off faster. And it cooled off before really plate tectonics were able to start on Mars. Fortunately, on Earth, we still have plate tectonics. And plate tectonics is the grand recycling system of our planet, recycling materials in the atmosphere, in the surface, and the subsurface. And Mars never had that.
plate tectonics also keeps Earth's temperatures moderate by recycling chemicals to keep the volume of carbon dioxide in our atmosphere uniform.
Lacking plate tectonics, it didn't have the persistence of Earth. It developed maybe habitable conditions and maybe complex multicellular life very quickly, and then it dies off because it doesn't have the long-term potential that plate tectonics gives the Earth.
Plate tectonics may be one indicator for Earth-like life. But evidence suggests there may exist another type of life on a moon that belongs to the Lord of the Rings. In 2004, NASA's Cassini mission conducted flybys around the gas giant planet of Saturn. A year later, the spacecraft released its Huygens probe into the atmosphere of Saturn's largest moon, Titan. The images revealed that Titan has similar features to Earth, such as weather cycles and volcanism.
Saturn's moon, Titan, is a very complex place with rainfall, rivers, and seasons, and meteorology, and a complex atmosphere, and interesting chemistry. Again, it's not going to be our kind of life, but there are flows of energy and organic compounds, and some other kind of life could flourish.
Radar imaging data has revealed the presence of liquid lakes on Titan. Although they're comprised of ethane and methane, they may be reminiscent of what water on Earth was like 4 billion years ago.
Titan, the moon of Saturn, is a really cool place, literally and figuratively. It's so cold that there's no liquid water. The ice there would be as hard as rocks, water ice, but there is a liquid methane, liquid ethane. So maybe there's life. Maybe life doesn't need liquid water. Maybe life can survive on another liquid methane.
Titan's temperature is a chilly -289 degrees Fahrenheit, but it has a nitrogen-rich atmosphere which produces hydrocarbons that can stay liquid at cooler temperatures. So it's possible that Titan may be hospitable to a new type of so-called extremophile, an organism that thrives in extreme environments. In the case of Titan, they may be psychrophiles, bacteria that thrives in frigid temperatures and uses methane to produce energy. Chris McKay has observed psychrophiles under ice-covered lakes in Antarctica. Some organisms live at the bottom of these waters, where their biological activities have created a zone devoid of oxygen and rich in organic molecules like methane.
One of the interesting ecosystems in the Antarctic are the ice-covered lakes, which have a persistent ice cover of about 15 feet of ice. Below that ice, there's liquid water. Given that there's water, it's not too surprising that there's algae and bacteria living in that water.
Like Antarctica, Titan's lakes may also contain similar extreme organisms that survive on methane. And Titan may not be the only moon harboring life. In 2003, NASA's Galileo space probe snapped pictures of Jupiter's moon, Europa. Evidence suggests liquid water may exist underneath its frozen crust. Scientists think Europa has an ocean that's over 50 miles deep. There are also signs of volcanic activity. So Europa's icy water could be warmed to a liquid state by volcanic vents on the ocean floor. And this volcanic activity would aid in cooking up chemicals necessary for life.
We have very convincing evidence that below the icy surface, there's an ocean. Ocean, water, maybe life. And we also have evidence that there are possible energy sources in Europa. So all the necessary ingredients for life seem to be there.
The ice on the surface of Europa is extremely thick, maybe as much as 6 miles deep. So it is unlikely that a human spacecraft will be able to drill down into its ocean anytime soon.
I think a realistic mission to Europa would be to search the surface for evidence of organisms that have been carried up through the cracks and deposited on the surface. They would be dead, but they would be biological and we could study them.
Our solar system is full of diverse, interesting places, and we shouldn't rule any of them out for life until we explore broadly, because we don't really know what we're looking for.
Armed with new technologies, astrobiologists have widened their search for extraterrestrial life. The next frontier includes our entire Milky Way galaxy and beyond. Astrobiology is pushing back the boundaries of modern science. Researchers now have the technological instruments to locate exoplanets. These are planets that exist outside our solar system. Exoplanets need to pass several tests in order to be considered suitable for Earth-like life. Most importantly, they need to be within a habitable zone of a central star like our Sun in order to support liquid water.
Our star is just right. It's not too hot and it's not too cold. And so we're just right in this perfect area where life was able to evolve.
In 2008, NASA plans to launch a space telescope called Kepler to search for terrestrial Earth-sized planets. The spacecraft's instruments will be able to detect exoplanets by measuring changes in a star's light curve as a planet passes between the star and the spacecraft. Jeff Marcy is one of the world's leading planet hunters.
We would estimate that there are some 50 billion, maybe 60 billion Earth-like planets within just our Milky Way galaxy alone. And remember, our Milky Way galaxy is just one of hundreds of billions of galaxies out there, more or less like our Milky Way. So the number of Earth-like planets in our universe is a nearly uncountable number.
But locating exoplanets is only half the battle for an astrobiologist. In the next 20 years, NASA will launch the Terrestrial Planet Finder. This collection of highly sensitive space telescopes will actually recognize if a planet has the right atmospheric gases, such as water vapor, carbon dioxide, methane, and ozone, all necessary to sustain Earth-like life.
With that picture, we can then take the light from that planet, spread it out into all of its colors or wavelengths, blue, green, yellow, red, even into the infrared, and analyze that light for the chemical composition, maybe even the biological composition of that planet. What we might find are signs of life in a variety of forms. For example, oxygen.
When it comes to producing larger Earth-like life, a planet or moon needs oxygen. 3.4 billion years ago, the only life on our planet were single-celled microbial organisms. But as this primitive life absorbed energy from the sun, it formed a green pigment called chlorophyll. This produced photosynthesis, a chemical process which converts carbon dioxide and water into energy, with oxygen as a waste product. Single-celled organisms evolved into cyanobacteria, one of the Earth's earliest structures. Cyanobacteria injected vast amounts of oxygen into the oceans and air. New life emerged, which diversified and developed into large multicellular species, and eventually, man.
Our Earth would not have oxygen in the atmosphere if it were not for plant life. By photosynthesis, generating the oxygen that otherwise would oxidize rocks and vanish. So, oxygen is a biomarker for the Earth. If we could examine another Earth-like planet and detect oxygen in its atmosphere, it would be one key sign, not yet definitive, but one element of the argument that that planet too has photosynthetic life.
At NASA's Ames Research Center, astrochemist Lee Biebout and her colleagues are cultivating oxygen-bearing ecosystems in a greenhouse. They're microbial mats, complex microbe communities often found on muddy and sandy sediment surfaces, in hyper-salty waters and carbonate beaches. These microbial mats are the oldest known living ecosystems on Earth. Biebout wants to know if these microbes could exist on other planets, producing oxygen, thereby enabling life to evolve.
We know that with the advent of oxygen production through photosynthesis, these microbial ecosystems, in particular the cyanobacteria, began to change our atmosphere. We're very curious how that happened, how that transitioned, how these microbes adapted and spread to diversify and fill so many niches on our planet. This is important in helping us decide what to look for on other places, say Mars or other extraterrestrial places.
If life exists far off in our galaxy, or in distant galaxies, will it truly be Earth-like? On our planet, all life contains DNA, a long chain of molecules that holds the blueprint for every living thing. It allows life to duplicate and branch out, essentially creating the tree of life. But are there alternatives?
Maybe life on another world is still carbon and water-based, but doesn't use DNA at all. Maybe it uses a completely different type of molecule to store information. That would be very exciting.
And could there be life that doesn't require DNA, carbon, or water?
Well, it may be that ours is kind of a crappy planet compared to what's out there, that there may be other planets that are much more optimized for advanced life.
Many of my colleagues, which are doing astrobiological research, they're looking for life that unkindly I might typify as stupid life. And they're looking for microbes mostly. There may be something a little bit bigger.
Some astrobiologists want a close encounter with something more than just a microbe. They're looking for intelligent life that's perhaps even smarter than us. The search for life extends beyond looking for slimy bacteria. In astrobiology, a crack team of scientists wants to make contact with something much grander.
SETI, of course, is looking for intelligent life in space, but it doesn't just stop there. They have to be not only intelligent, but they have to be technologically competent.
The Search for Extraterrestrial Intelligence Institute, better known as SETI, uses radio technology to listen for radio leaks from alien civilizations. It's based on the premise that humans need to communicate, so perhaps alien nations also want to get their message out.
What we try and do is simply try and eavesdrop on signals, either radio waves that we could pick up with our antennas, or flashing laser lights. They might be using big lasers to aim pulses of light in our direction. I am not man, I am microbe. I'm also Seth Shostak for the SETI Institute, whose mission is to understand the nature and origin of life in the universe.
And I'm Molly Bentley. Welcome to Are We Alone?
Who remind you that there's more to life than just what you find at your local zoo.
At SETI, senior astronomer Seth Shostak hosts a regular radio show that's podcasted,
where we're bugging out with microbes.
There are so many cohabitating with you. You're listening to Hand Me Microbe.
Shostak broadcasts lively, yet informative science-related news to Earthlings, as well as other advanced civilizations that have the means to listen in.
Cynthia Phillips, thanks for joining me today. We are so fond of radio for listening that we started a weekly radio show in which we, in a sense, broadcast. But a lot of people are interested in SETI because everybody's interested in aliens in the same way that just about everybody's interested in dinosaurs. People are just interested in that. So we're trying to take advantage of the fact that they're interested in what we do to get them interested in some broader subjects in science and also technology.
SETI has been listening for signals since the 1960s, but ET hasn't phoned in. This silence has fueled skepticism.
Now we're going to find lots of planets with life. I'm guessing that intelligence will be rare, but they won't be smart in the way that humans are smart. That's going to be rare. But again, that's just my intuition.
Aliens can't get here at faster than the speed of light. Physics doesn't allow that. And that means since we've only been broadcasting for, say, 60 years, they can't be coming from a planet more than 30 light years away. Well, the number of stars within 30 light years is pretty small.
Our universe is over 12 billion years old. Planet Earth has only been around for over 4.6 billion years. Therefore, there are planets millions and billions of years older than us. So if there's life beyond the Milky Way galaxy, it potentially could be millions to billions of years more advanced than us.
I think that the truly intelligent species out there, if they ever happened upon us, would maybe regard us as we regard ants or bacteria, as some primitive example of life. Anybody we meet is going to be much more advanced than us, at least certainly much more aged than us in terms of how long they've been a civilization.
If intelligent civilizations do exist beyond Earth, what would they look like?
But if we find intelligence in space, it's moved on beyond biological intelligence and moved on to machine intelligence. A thinking machine that represents 1 million years evolution beyond where we are, who knows how it's built? All you know is that it might be really, really smart.
There's no logical reason why there shouldn't be machines from other worlds exploring our planet, coming into our airspace, maybe even attempting to interact with us in some way.
Whether we find a trace of bacteria or a high-tech civilization, any discovery of life will revolutionize the way we think about the universe and ourselves. Until then, it remains one of the greatest unsolved mysteries of all time.
So we're going to see a real zoo out there when we finally do discover alien life. All sorts of different ways of coding information and making molecules, causing the phenomenon of life.
The people that work on this field are geeks, so we imagine making contact with alien geeks, right? And that we're going to have fun talking about equations together, but maybe we'll end up making contact with alien hipsters or bohemians, and we'll need some other form.
So, life as we don't know it. Thanks very much for talking with me. I'm Seth Shostak for the SETI Institute, where we always listen, but occasionally we broadcast.
In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
It promises to deliver technologies that will carry us ever farther and ever faster. But it's fraught with constant and lethal peril.
Flying in outer space is like going through a shooting gallery.
It will test the limits of human capacity and human ingenuity.
If something goes wrong, what do? Nothing. You just die.
Welcome to the age of space travel. In ways scarcely even imagined, the steady hand of progress is poised to deliver humanity to the heavens. For ages, the mysterious splendor of the universe has enticed us from its remote heights. At last, its mysterious temptations are within reach, and man's destiny can be fulfilled.
I don't know if it's written in our genes, but anytime you see something at a distance and it piques your curiosity, the first thing you want to do is get a closer look. So while telescopes get you pretty far in this regard, those things that are sort of close enough to be within the reach of our space program, why not take the trip?
T-minus 10, 9, main engine start, 5, 4, and liftoff of Space Shuttle Atlantis to assemble.
Prying free from our home planet's grip ranks among the greatest of human achievements. But no one since 1972 has ventured beyond the Earth's orbit.
Our space program has been stuck for 30 years. We simply just go around the planet Earth. It's just like Columbus exploring the New World for the first time and then spending the rest of his life simply puttering around the Spanish coastline. What's the problem? There's a dirty little 4-letter word, and that is cost. It costs about $10,000 to put a pound of anything into orbit. Imagine John Glenn made out of solid gold. That's what it costs to put John Glenn or you into orbit. It would cost about $20 million for you to take a weekend trip up to the space station. It would cost about $500 million for you to go to the moon. And for you to go to Mars would probably cost tens of billions of dollars.
One way to reduce the cost of reaching space would be to find a more efficient way to overcome Earth's gravity.
Remember the story of Jack and the Beanstalk? Jack was the little boy who climbed the beanstalk into heaven. Well, imagine a space elevator such that you hit the up button and the elevator takes you into the heavens just like Jack and the Beanstalk.
Instead of building from the ground up, the space elevator would be built from the top down. A satellite in geosynchronous orbit would drop a 60,000-mile cable back to Earth, where it would be anchored to the surface.
Now we are within striking distance of being able to create fibers that can withstand the tension of traveling at enormous velocities in outer space as the space elevator rotates with the planet Earth. So it never falls because it rotates at the same rate as the planet Earth.
The elevator's compartment would simply roll up the cable, shuttling travelers and supplies into orbit, where it would wait for a spacecraft. This system would entirely replace a conventional rocket launch.
And that might reduce the cost of space travel by a factor of 1,000. Think about that. Then you begin to realize that perhaps a trip to outer space may be no worse than an airplane ticket.
But beyond the limits of Earth's comforting embrace, exotic menaces await every space traveler.
Flying in outer space is not like taking a nice ride in the country in a car. It's like going through a shooting gallery.
To an unsuspecting voyager, it might seem the universe is taking aim with a firearm.
There are particles in space, even dust-sized particles, pebble-sized particles, that are traveling tens of thousands of miles an hour and sometimes even faster.
More than 500,000 of these projectiles, measuring over an inch in diameter, are zipping around our planet right now. They include pieces of glass broken off of solar cells, paint chips from spacecraft, and debris from rocket booster engines. And in deeper space, there's more danger from pebble-sized meteors called micrometeoroids.
A small piece of dust can crack glass, it can penetrate metal, it can pulverize plastic. And that does happen in space all the time.
But perhaps an even more deadly danger, not at all solid, lies in wait: radiation. The devastating effects of this invisible energy have been witnessed on Earth in the aftermath of the atomic bombs of World War II and the nuclear fallout of Chernobyl. Distressingly, our own life-giving sun spews out streams of poisonous radiation.
So realize that we've been protected in this cradle. We've been protected by the atmosphere of the Earth. Magnetic field of the Earth gobbles up most of the flares from the sun to create the aurora borealis. In outer space, you get the aurora borealis coming right at you. There's no ozone layer, there's no magnetic field to protect you. It's just you and the harshness of outer space.
At our home planet's distance from the sun, roughly 90 million miles away, several 100 million solar particles pass through each square inch of space every second around our Earth.
There's high energy particles streaming from the sun all the time. But every now and then there's an extra dose of these particles. The sun burps up high energy radiation. That's bad too. That level of radiation is never good for one's DNA.
Sunspots flare up these extra doses of energy, like a battery of cannons bombarding the cosmos.
There's no way to know that they're going to be here before they arrive.
Unfortunately, there's still a risk of radiation even as we get farther from the sun. That's because another invading energy lurks. Known as galactic cosmic rays, they hail from the distant alien worlds of exploding stars and black holes.
Galactic cosmic rays are particles that are traveling at speeds very close to the speed of light. Even a single particle of iron slamming into your body can have the effect of a Major League Baseball at 100 miles an hour. They can be devastating.
Although heavy iron particles are rare, outside of the protection of a spacecraft, such as when an astronaut performs a spacewalk, thousands of galactic cosmic rays do penetrate the body every second. Every 24 hours, the galactic cosmic rays and solar particles attack a space traveler with as much radiation as a surface dweller on Earth receives in 6 months. The human body won't immediately feel the impacting radiation, but in sufficient quantities, it can be noticed. Even with eyes closed, the particles spark flashes when they strike a space traveler's retina.
The flashes are not blinding, and you have to ask yourself, did I see something? And then you say, oh, yes, I did. And its appearance is a little different from time to time.
However, the human body does feel the shock of this bizarre weightless existence.
I think that the most dangerous thing going into space is the loss of gravity. Weightlessness causes almost every system in your body to start changing. and it doesn't stop changing until you get back onto a world where you're pulled down again by its gravity.
One of the first casualties of zero gravity is a space traveler's sense of direction.
What's up and what's down? Very good question. And first of all, it's whatever you want it to be. If you want this to be up, that's fine. But if you want this to be up, that's just as good.
Most travelers will suffer from motion sickness for the first few hours, or most likely, days.
It's just one of those things that you ought to resign yourself to facing, that everyone is very likely to feel a little bit disturbed in terms of orientation.
Here on Earth, scuba divers floating underwater experience the nearest sensation of prolonged periods without gravity. It is for this very reason that aspiring NASA astronauts train to live and work in a gravity-free environment by subjecting themselves for up to 6 hours at a time in a large water tank.
Now, scuba equipment, you still experience the forces of gravity, but it doesn't feel like it because your whole body is uniformly buoyed by the water that holds you up.
And except for the visual cue of air bubbles floating to the surface, swimming underwater can mimic the sensation of disorientation. But as time passes in the weightlessness of space, the human body senses it no longer needs to resist the force of gravity and begins shedding muscle and bone mass.
When you're in space, your body thinks you might as well be lying in bed. And so if you're not careful, your body will atrophy.
To counter this, each day in space, an astronaut needs to exercise. The legs are especially vulnerable because they are seldom used. In this world, the arms and hands do most of the work to move the body around.
What would be the toughest thing to get used to might very well be just how you live in space, where you can't walk across the room. You have to float everywhere you're going.
The lack of gravity also slows down the digestive tract, which can cause problems at mealtime.
Your digestive system stops. You can't eat, you can't drink until you can start digesting again. And that can take anywhere from hours to days.
Worse still, zero gravity and radiation can combine in an especially sinister way.
In space, the immune system is not as effective as it normally is. And many of the bacteria and viruses that we normally can withstand become more virulent.
Additionally, bacteria can grow up to 50 times faster, and any virus brought on board could mutate into a never-before-seen predator, thanks to the ever-present radiation. All these difficulties prey on space travelers in just the first few hours or days. And what about journeys that need more time? It only gets tougher. The universe is an unforgiving place. It's open to only the boldest adventurers, those who have the mettle to trek deep into an environment swimming with toxic hazards, and unafraid to stray far from the safe and familiar.
We take it for granted that clothing is flexible and machines work in room temperature, because implicitly or explicitly, they're designed for that. You go into the depths of space. If you're facing the sun, it could be hundreds of degrees Fahrenheit. If you're facing away from the sun, it could be hundreds of degrees below zero.
Down here on Earth, you take so much for granted. You know, we're out here, sunshine, the fresh air all around you. Up there, you're in a closed ecosystem. You have to supply all the human needs that the Earth just, automatically does for us. You have to hope that the integrity of the hull stays together so you don't have rapid decompression, quick suffocation.
The same reality exists for a submarine gliding deep through the ocean. It provides a life-preserving barrier to protect its inhabitants from a surrounding alien world.
If there's damage to the spaceship, air leaks out, you die. Damage to the submarine, water gets in, you die. So the isolation, both physically and personally, between the two seem quite parallel.
The potential for a catastrophic mishap lurks.
When you're out in the middle of the ocean, you have only yourself and your colleagues to rely on. And the same thing applies in space.
Things have to hold up. You can't come back, you can't run to the hardware store, you can't fix the thing with some part that you didn't bring along, and you're stuck with human ingenuity, the tools you brought with you. And out there in space, you truly are just removed from mankind. It is isolation like I've never felt before.
Liftoff, we have liftoff.
Often, our efforts to explore space have been analogized to the great explorers of the 15th and 16th century. The first to sort of cross the oceans, going to unknown territory, having to bring all their supplies with them, not knowing if they'll ever return. And I think there's a lot to say about that analogy, but there's a point where it breaks down badly. When Cortez landed in South America, when Columbus hit the Caribbean, there was still air there for him to breathe, all right? There were fruit on the trees. Suppose the Apollo 11 astronauts, Neil Armstrong and Buzz Aldrin, landed on the moon and, like, the engine broke.
Okay, Houston, we've had a problem here.
What do? Nothing. You just die. There's not sort of an engine tree that they can pluck parts from to repair their ship. So the hazards are vastly greater to human health in space exploration than traveling anywhere on Earth's surface.
There won't be any service stations in case you break down, run out of gas, or need something to drink.
One of the challenges of space exploration is either carrying along with you all the supplies you need, water, food, oxygen, or finding some way to manufacture that en route or at your destination. We're not there yet. We don't know how to do that yet. And so one hazard is if something goes wrong and you run out of food and water and shelter, that's bad. You'll die.
Every sip, every drop of water is precious. On a space voyage, there will be no such thing as a shower. The only option will likely be a wet cloth. This is quite a change from the 130 gallons of water each American consumes in just one day. The cuisine on board would take some getting used to as well.
For a few days, you can take fresh fruits and fresh vegetables, carrots and apples and things like that. For the longer missions, though, you have to have storable foods that can, stay for long periods of time without spoiling and going bad.
And yet, astronauts agree that enduring the myriad of risks is a small price to pay for the chance to witness the wonder of the cosmos in person.
1500's 2.3.
I know how they felt because they report things like, well, you could hold up your finger and you could block out the Earth with your thumb. And it kind of gave them an entire new perspective of how amazing this little blue marble the Earth is and how precious it is in this vast solar system.
That experience changed me forever, and I think it would change anyone that could possibly have that experience in the future.
However, the length of future voyages might limit the range of experiences available to space travelers. Distances in our vast universe can defy comprehension. If our sun were the size of a basketball, our Earth would be the size of a pea. If they were placed in Central Park, the nearest star would be another basketball almost 5,000 miles away in Hawaii.
one of the prerequisites you might have for a space mission is that you're alive when you arrive at your destination. So you'd want your space missions to be small compared with the life expectancy of a human being. And right now, that pretty much limits us to the planets and possibly comets and asteroids, if we include those as places we might visit.
The brutal, scathing landscapes of the solar system's inner planets, Mercury and Venus, do not make for tempting vacation destinations. Temperatures on Venus can exceed 900 degrees Fahrenheit, and the crushing air pressure is equivalent to being submerged in 3,000 feet of water. That leaves all points further out from the sun for potential exploration. But even trips to our closest attractions will still take several months or even years. About 139 million miles separate the orbits of Earth and Mars. But since each body circles the sun at different speeds, the distances with respect to each other change continuously.
The problem with going to Mars is that Mars and the Earth only line up about once every 2 years.
With current chemically propelled rocket technology, a flight leaving from Earth for the Red Planet in 2018, when the two bodies are on the same side of the sun, could take 104 days, less than 4 months. After a 40-day stay, the return trip would require a little more than 6 months. That's an entire year to make one round trip. But a voyage departing in 2031, when the Earth and Mars are on the opposite sides of the sun, would demand about 20 months, nearly 2 years of travel time. That's 1 to 2 years away from any lifeline. Comets, those oversized dirty snowballs, swoop close enough to Earth to accommodate a round trip lasting as short as a few months.
Find some comet that's on its way into the sun and ride it. And watch the coma grow and the tail form. And watch the sun first slowly, but then rapidly get larger and larger and larger. You swing around the backside and come out. It's got to be the most fun tour of the solar system you can come up with. It'd be dangerous because particles of the comet would fly up and hit you in the face and things. So apart from all that which would kill you, it would be a fun trip.
Just beyond the orbit of Mars, asteroids fly within range of a few years round trip from Earth. Future travel agencies might arrange cosmic versions of extreme vacations by exploiting the unique environments of these miniature planets.
They put you on a sled and slingshot you into space in such a way that the weak gravity of the asteroid will hold you in orbit but won't pull you back down again. Would be a great ride.
3 times farther away than Mars, the orbit of Jupiter, with its crowded moon system, offers dozens of diverse visions. It may prove tempting for future travelers, but a round trip could take 5 years. Saturn is nearly twice as far as Jupiter, and the thought of decade-long trips might be too much to bear. But there are technologies that can slice the time it takes to visit Mars to just a few days. For mankind ever to venture into the depths of the cosmos, endeavor to bathe in the light of an exotic star, or even just a voyage to the suburbs of our own solar system, we'll need to find a way to travel much, much faster. What's the fastest we could travel? Nothing yet observed by science moves faster than the speed of light, 186,000 miles per second.
The speed of light is the ultimate velocity in the universe. It's Einstein's cop on the block. The speed of light is so fast that you could go around the Earth 7 times in just 1 second. For you to jump to the moon at the speed of light, you could reach the moon in about 1 second.
Compare that to the 3 days it takes to get there with current technology. The problem is that we can't travel at the speed of light, or really anything even approaching it.
Take the fastest thing we have ever sent anywhere and ask, how long will that take to reach the nearest stars? That would take 50,000 years.
And that is using current chemical propulsion, which maxes out at about 40,000 miles per hour. The same power source we use to lift our rockets off of the planet. But getting us to Mars faster than a few months' time would require a different kind of propulsion. There are a few ideas for how to propel us to velocities closer to the speed of light, which would be fast enough to get us anywhere in the solar system in under a day, or even to the nearest stars in less than a decade. One such theory echoes an ancient earthly propulsion device, wind pushing a sail.
It was Kepler, that great astronomer, who first wrote down in his notes the possibility of using sails to sail in outer space.
Light streaming from the sun mimics gusts of wind in outer space. This solar wind is what creates a comet's tail as it nears the sun. However, sunlight scatters in all directions, and as the distance from the sun doubles, its power reduces by a factor of 4. With a little help from the moon, there is a manner in which light could be focused in one direction.
If we have a battery of laser cannons on the moon, firing in synchronization at a solar sail, we may be able to propel it to about perhaps half the speed of light. Now, lasers do diffuse with space. For example, if I have a laser on the Earth and I shine it to the moon, it does not create a spot on the moon. The spot is about 5 miles across on the moon. These sails, however, would be huge. Now we're talking about astronauts, perhaps spending months in outer space, designing a sail hundreds, maybe even thousands of miles across, sufficiently light and durable in order to capture light from a battery of laser beams on the moon.
But solar sailing limits space vessels to destinations within our solar system. One alternative gets around this problem by tapping into hydrogen, the most abundant element in the universe, as a propulsion source.
My favorite design to take us to the stars is the ramjet fusion engine. The ramjet engine has a gigantic scoop in the forward direction that gobbles up hydrogen gas as it moves in deep space. It collects the hydrogen gas and then fuses it, just like the sun, and shoots out a huge stream of ions out the other end. And on paper, it looks fantastic. On paper, it looks as if a ramjet fusion engine could go on forever, simply using up the hydrogen that is found naturally in outer space.
Unfortunately, scientists have not yet been able to achieve a hydrogen fusion reaction capable of propulsion in tests. But another potential fuel source, one that seems to come right out of science fiction, has already been created in laboratories. It's called antimatter, and it's the opposite of all that we know.
For example, think of the world on the other side of the looking glass. Just like in Lewis Carroll's Alice in Wonderland, we physicists have wondered, is there another universe on the other end of the looking glass? A parity-reversed universe where left becomes right, right becomes left. In an anti-universe, charges are reversed. So positive charges become negative, negative charges become positive, and when they meet, they create a burst of energy. So if this universe on the other side of the looking glass were made out of antimatter, and I were to touch this other universe, I would destroy most of the New York City metropolitan area in a burst of energy. So the conversion of antimatter and matter to energy is 100% efficient. It is the ultimate engine. But there is a catch. There's always a catch. Even though we can create anti-atoms in the laboratory, the cost is stupendous. It would bankrupt the United States of America to create a teaspoon of antimatter. However, it would only take a few grams of antimatter to take us to Mars, and perhaps several teaspoons of antimatter to take us to the nearby stars.
But for us to ever visit a distant star or another galaxy, we need something stranger than even Alice could ever dream of, peering through her looking glass. Scientists continue the quest for a propulsion method to carry us ever deeper into space. But even achieving light speed won't allow us to get very far.
Light's fast, but the universe is huge. So even if we could ride on a beam of light, if we wanted to cross the galaxy, the way they do in all the science fiction programs, it would take 100,000 years to do it.
And even at light speed, traveling to the nearest galaxy would take several million years. And if light speed is the ultimate speed limit of the universe, it seems we're doomed to confinement in our galactic neighborhood.
What we're desperate for is some new understanding of the fabric of space-time that will allow us to somehow warp it, distort it, so that you can take shortcuts. And of course, that's what they do in Star Trek when they turn on their warp drives. They want to get from one side of the galaxy to the other. All they do is invoke the warp drive that warps the fabric of space, and then they take a little shortcut right there. They cheat, basically.
Everybody knows Einstein's famous dictum, you cannot go faster than the speed of light. However, there's a footnote to it. You see, Einstein left open the possibility that you can fold the fabric of space and time itself so that you effectively take a shortcut through the universe. Think of a carpet. If you want to go across the carpet, that's the old-fashioned way. You can also get a lasso a table on the other side of the carpet, and then drag the table toward you so that you collapse the space in front of you. In a nutshell, Einstein says the bigger the mass, the bigger the bending of space and time. If you can concentrate enormous amounts of energy at a single point, comparable to that of a black hole or a huge gigantic star, you are literally warping the fabric of space and time. You simply hop across to the nearby stars. So in other words, you did not really go to the stars. The stars came to you because you are compressing the space in front of you.
The massive amount of energy or mass needed to create such a warped curvature of space seems beyond comprehension and perhaps beyond human capability. There may be an alternative. Physicist John Brandenburg is developing a theory in which a starship of the future could achieve faster-than-light travel, not by manipulating a vast area of the universe, but rather by manipulating only the area around the starship. The trick is to have a starship imitate a curious particle that so far only exists in theory. It's called a tachyon.
It's a particle with a different twist. Light itself always moves at the same speed. Tachyons, on the other hand, can go infinitely fast. They just can't go slower than the speed of light. They look at the speed of light as a lower speed limit that they cannot violate.
If they do exist, tachyons can outrun the speed of light because they have what physicists recognize as imaginary mass. An imaginary value can be visualized in the spin of a struck tennis ball. Its spin can cause it to bend and move in a manner that an observer might not expect to see from its initial point of contact. In the same way, a tachyon is unseen by the universe and can break its speed limits. Brandenburg proposes altering the space-time surrounding a starship with a powerful electromagnetic field so that the ship moves through space like a tachyon. It would operate like a stealth aircraft, invisible to radar, unseen by radar operators.
So if one can achieve this control of the space-time around this ship, one can essentially make it an imaginary object. In a technical way, that means it's moving faster than light. You're basically disconnecting yourself from the rest of the cosmos.
It could grant the traveler the ability to go anywhere in the universe in the blink of an eye, as if a multitude of doorways suddenly appeared.
A doorway you step into and then you step out somewhere down the hall so fast that it didn't seem like you had time to move any place. That's an imaginary connection in space-time. And you've changed yourself, not space-time.
No one may know how fast or even where such a space vessel could travel.
Which door to go into, which door to come out of. That's the trick.
But voyaging through the Hall of the Universe isn't possible without first overcoming one of its fundamental forces, the one that shackles us to our home planet.
Getting away from the Earth's gravitational field. That's the first thing that we have to do.
10, 9, 8, 7, 6.
For an object to
5,
break away from Earth's gravitational
3,
pull,
2, 1. We have ignition and liftoff of NASA's New
it must
Horizons.
achieve a velocity of 17,500 miles per hour. That's fast enough to streak from New York to Los Angeles in about 8 minutes.
There's no other way to do it, at least that we have now, other than brute force.
While a theoretical space elevator can climb away from Earth's gravitational pull, a rocket must outrun it with the brute force provided by the explosive chemical reaction of burning fuel.
Chemical power is what drives today's rocket engines. Every time you burn something, that's chemical power. Every time a rocket engine ignites, that's chemical power. Every time you start your engine in your car, you're using the chemical energy stored in the gasoline.
The fuel alone can burden a spacebound craft with up to 90% of its total weight.
If you're carrying all the fuel you'll ever need, then most of the effort of the first ignited fuel is to lift the unburnt fuel into orbit. It'd be like trying to drive from New York City to Los Angeles on one tank of gas. Well, you would need a tanker truck behind you. And most of the energy to accelerate the tanker truck is going into just move the fuel that's in the tanker truck.
The space shuttle, its rockets, and the fuel they're carrying weigh a staggering 4 million pounds. And nothing short of a bone-rattling eruption could push it up and away from Earth.
Well, Brent, looks like your long wait is over. We wish you all the best luck in the world. Godspeed, and we'll see you back here in about 2 weeks.
A journey into space today means that space travelers must ride a controlled detonation into the sky.
Whatever the vehicle weighs, we have to generate about 1.5 to 2 times that thrust in order to get it off the surface of the Earth.
To get the space shuttle up to speed demands 7 million pounds of thrust. To put that into perspective,
if you can imagine me holding a 1-pound ball in my hand, if I'm holding it here and I'm holding it steady, I am exerting a pound of thrust on that ball. So if I lower it down, I'm clearly not exerting a 1 pound. If I pick it up, I'm exerting more than a pound. So you have to have a little more thrust than you do the weight, obviously, or you won't go anywhere.
how a rocket moves can be illustrated with a blown-up balloon.
This works almost like an engine nozzle. Now I can hold it in place, and you can control it. You can let it go. And what we do is we try to eject as much mass through that throat as we can. And as it expands out, the back end, that expansion or that pressure pushing that way pushes the vehicle this way.
When today's astronauts climb aboard for their journeys on the space shuttle, they're hitching to giant containers housing that necessary mass. Millions of pounds of highly combustible hydrogen and oxygen wait to be ejected. It only takes a spark.
The main engine starts 6 seconds before takeoff. The whole shuttle shakes. It feels like it wants to just rip itself out of the launch pad.
Off of Space Shuttle Endeavour, expanding the International
It shudders,
Space Station.
and you think, oh my gosh, that's an awful lot of force, about 1.5 million pounds of thrust. It's kind of surreal. It's like, this can't really be happening. It's something you've been wanting to do for years and years, and it's really happening. It's like riding a man-made earthquake. You've spent several million pounds worth of fuel to get to the first 2 minutes of flight, and then the solid rocket boosters come off. That's like a train wreck when those things come off. It almost feels like you're just accelerating faster and faster and faster as you burn all the fuel out of the big main tank. So for the next 6 minutes, you're accelerating up to a point where you're finally feeling about 3 Gs, 3 times the force of gravity of acceleration. And so now it almost feels like there's a big gorilla sitting on your chest.
A drag racer who accelerates from 0 to 100 miles per hour in 2 seconds will feel G-forces similar to those experienced by astronauts.
As the vehicle keeps accelerating and you're watching the speed tick by in thousands of feet per second until you get to 25 times the speed of sound. Then there's a cutoff, and then everything's floating. And now you're in space. So space isn't very far away. It only takes about 8 minutes and 30 seconds to get there.
The next model for venturing into the great beyond and reaching new worlds will begin first with a visit to an old friend. Although not quite yet a space elevator, NASA's mission to return to the moon builds on the idea of Earth orbit as a base for farther voyages. NASA's Constellation program, a successor to the legendary Apollo program, aims to plant boots on the moon by 2020. 2 separate rockets form the foundation of the plan. The unmanned Ares 5 rocket, towering taller than a football field standing on its end, will carry the lunar lander, supplies, and an Earth departure rocket into orbit, where it will wait for the astronauts. The Ares 1 rocket will deliver the crew to orbit aboard a capsule. It will then rendezvous with the Earth departure rocket and blast to the moon.
We can take more supplies, more commodities to the moon. That's what this tandem system provides for us. Instead of Apollo, which only allowed us to go for 1 or 2 days at a time and then come back.
Will we ever find a way to surpass the bold achievements of the Apollo program? Will we ever cross the vast expanse of the cosmos as quickly and effortlessly as we travel to another city or another continent? We must if we are to survive.
So I can imagine, and this is just my wild fantasy, some analogy to world music far in the future where we're mixing our musical cultures with alien musical cultures. I think you'll get many different shades of astrobiology if you talk to different scientists, but I think you'll get a lot of agreement on the broad goals. We want to find life elsewhere, but in the meantime, we're learning a lot about the history of life on Earth.
In the field of astrobiology, one of the fundamental goals in searching for life elsewhere is first figuring out how life evolved here on Earth.
One of the big unsolved mysteries in astrobiology, of course, is how life got started on Earth. Because if we could understand that, then we would have some insight into whether it could have gotten started elsewhere.
Earth orbits in what's called the habitable zone. It's a region of space where conditions are favorable for life forms that we know can be found on our planet. We are at just the right distance from the sun, so our oceans don't evaporate. Our temperatures are not too hot or too cold. And we have oxygen in our atmosphere, so we can breathe. Earth's been a cosmic paradise for all types of life, from small single-celled organisms such as bacteria to large multicellular mammals, including man.
In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
It's perhaps the holy grail of planetary science.
Are we alone in the universe? It's one of the grandest questions we could answer.
We don't really have a definition of life, but I think I'll know it when I discover it.
Life can take many twists and turns, and I think the really cool thing about it is the variety that we're going to be able to find elsewhere.
Are we a lonely planet? Or does life exist beyond Earth? Members of the groundbreaking field of astrobiology have joined forces to solve this enduring mystery. Life. Is it rare in our universe? Or is space a galactic zoo, teeming with all sorts of creatures? It's believed that all life on our planet descended from a single common microbial ancestry, approximately 3.4 to 3.8 billion years ago. But how that microbe came into being remains puzzling. One way to search for answers is to look for ancient rocks where microbes leave trace evidence of their existence.
Geology is a crucial tool for understanding the origins and evolution of life on Earth because the historical record of life on Earth is almost entirely recorded in the rocks that we walk on.
Geologist Abigail Allwood's journey to discover the origins of life took her no farther than her own backyard. The Pilbara region of West Australia contains some of the oldest rocks on our planet. They're almost 3.5 billion years old.
The Pilbara contains rocks from the early Archean era that have survived on the Earth today. They contain several rock units that contain possible evidence for life.
Planet Earth has been around for over 4.6 billion years. But most of its original surface has been obliterated by plate tectonics and erosion. The extremely thick crust in the Pilbara has helped it resist destructive geologic processes.
The Pilbara hasn't been...
Everybody has this sort of iconic view of the aliens. They're going to be little gray guys with big eyeballs and small noses. Well, maybe, but I don't think so.
On far-off planets, life may be as far out as buggy-eyed microbes or sci-fi sea monsters like galactic manta rays. Others may be home to cybernetic organisms, hybrids of biology and machines.
One way to get a handle on thinking about super advanced aliens is to try to imagine the possibilities of our own future. Maybe it'll be machine-enabled humans. I feel like I've already become a machine-human hybrid. I mean, I have this laptop computer that I take with me everywhere, which is really kind of the third hemisphere of my brain. My body's even changing and becoming sort of shaped like a person using a laptop computer, and so I'm becoming Homo laptopicus. It's likely that the universe is full of life. We don't have evidence yet that we're not alone. So we're out there and we're looking.
When it comes to hunting for alien life, planetary scientist and musician David Grinspoon walks to a different beat.
I do wonder, in terms of extraterrestrial life, whether they'll have music or something like music. Music is fundamentally waves and rhythms, and that's sort of the nature of our universe. There is a certain musicality of just the fact that it's all vibrations and waves and rhythms and modulated tones.
Strongly affected by plate tectonics, and the original features in the sedimentary rocks are more or less ready for us to interpret. There are also sedimentary rocks of similar age, almost 3.5 billion years old, in South Africa. So far, the Pilbara seems to have yielded a richer fossil record.
Allwood spent more than 3 years surveying some of the rock formations in the Pilbara, examining unusual structures called stromatolites. Fossils formed by living organisms 3.5 billion years ago.
We realised that what we were looking at was the remnants of an ancient reef, a microbial reef. It's not a reef made of coral like we're familiar with today, but a reef made of stromatolites, structures formed by microorganisms.
Stromatolites are rocky structures that form on the sea floor, where fine layers of sediment are built up into cones, domes, and other shapes over a long time with the help of tiny organisms. A stromatolite is not alive, but is a structure made by living things. When we find one in the fossil record, it is like finding the footprint of long-dead microorganisms. But the microbes themselves are almost never preserved as fossils inside the stromatolites. And without that, it is extremely difficult to be sure an ancient stromatolite is proof of life. But in this case, Allwood found that the Pilbara stromatolites are in